Swayam Prabha. Digital India. Educated India.
Okay, so no problem. Like it was just after a session, so I think we don't have. Okay, so we are starting. Good evening, everyone, and welcome to this session on advanced process safety. Two in-person presentations, and the last one is BSc Beaker presentation that will be virtual. So the first presenter is Funky Lee, right? And from Yongji University, South Korea. So he's going to talk on the topic CFD-based target modeling and MINLP for optimal detector placement, guaranteeing minimal leakage. Right. So
to read and registered students of Yoshi University. Today I will present the technology-based target modeling and MIL for optimal detector placement guaranteeing leakage. First is overview, so background the report, and I will present the research objective. And I introduce the purpose method, detector placement optimization, and survey model. And next is implementation, features, and conclusion. First, chemical leak accidents are major industry and cause a lot of facilities. As you can see in the table, all the mitigation action and evacuation are the key to minimize the damage of the leak accidents. As you can see, so that was the minimum mitigation actions, the very little injuries. So systemic response for chemical leak accidents is necessary to mitigate the damage of leak accidents. However, without damage impact assessment, detectors are installed according to simple distance-based legal standards. Here is the distance-based criteria for detector placement for each country. The first one is portion die is in Korean. The portion die is stick is the one detector every 10 meters or close. And NFK and CPS they set the criteria for detector placement based on distance. So we need to establish a prediction system for quantitative damage prediction. Next is related work. So first is let's research the stochastic programming for minimizing average detection time for all scenarios. We use their objective function like that. They want to minimize the detection time. So their stochastic programming, they propose the stochastic programming for detector placement using their safety-based dispersion model. And the next thing is Yongji University's research, so placement optimization and the list of stationary and mobile sensors for chemical plant line monitoring. So different is two researches. They set up the sensors like the plants outside there. The next research is set of sensors inside the plants. Next thing is dynamic programming with dispersion model to estimate the risk of toxic gas leak scenario. They also use the simple Gaussian pool models to evaluate the risk of gas leak scenario. And the next thing is dynamic programming and use their CFD simulation for evaluate the risk of leak scenarios. So we can say the problems though. In the case of optimizing the placement only in accordance with the legal standards, it is difficult to systemically respond through damage impact assessment. So, and in the case of risk-based optimization, it takes a long time to calculate because the safety simulation is used in most cases. So, want to establishment of a prediction system for quantitative behavior assessment and reduce calculation time through deep learning-based surrogate model. Here is our flow chart. The first is the surrogate model, and we make the simulation data, the XYZ axis, and the time concentration of the gas. And we use this data to make optimization. We set the detect cost, like cost or budget. We set the constraints, and we do high-level-based optimization, and we extract the sensor's optimal position. Here's our object function. Our object function, similar with the prior research, Lex research, and we want to minimize the risk and the risk score. Here is RAI means the risk when scenario is A is detected by detector I. So we want to minimize the risk of the risk scenarios. And so next, we define the risk as this. Risk is the probability of scenarios and time when scenario was covered by detector I and multiply the damage when the scenario occurs. So currently, we set the D value is the same. So we show the sample of this framework. So, and also we set constraints such as detect cost and budget. And we use the Python as an optimization tool. The Python is Python-based open source software. It supports the diverse set of optimization capabilities for formulating and solving and analyzing optimization models. And we set the candidate sensor location. Currently, we set the regular intervals, the sense positions are set at regular intervals. So the user do not need to set the candidate position. So if the user wants to set the candidate sensor location, it can be, but now there is no need to set candidate sensor location. And we use the physics-based deep learning for surrogate modeling. Here is a curious question. The most physics numbers can be broken down into a sequence of vector and matrix operation or state of DL frameworks, deep learning frameworks of these. So why don't we just use these operators to realize physics numbers? So in this research, we use the differential physics and neural networks. The differential physics means the differential numerical simulation of physical systems and application of gradient-based method to the learning control of the physical system. And it also can be converted to Jacobian matrix, so it can be applied to neural network. Neural network do the numerical errors that occurs when discretity continues PDE. So the neural networks cannot minimize the numerical errors. So we propose the hybrid method for structural model. The first PD solver, we measure the differential physics and edit the neural network. So we use a PyFlow as a tool of the first PD solver. PyFlow is a fully differentiable Eulerian PD framework, and we use the simple Boyle-Swift model to test for approximation, and we also the Navier-Stokes for simulation like that. We use the two boundary conditions, equal for velocity and Newman boundary for pressure. And here's our implementation method. The first is we use Larkin field sampling as a build of the input data. Obtain a simulation input samples that do not overlap as much as possible using LHS. We expect the wind's direction and speed or leak slopes if the coordinates, etc. And we create the fit scenarios through surrogate model. Here is the sample of LHS. You can see the red dots from Monte Carlo. They purchase the random rate, but LHS do not overlap as much as the possible. which we collect the data like that. And here's our solid simulation. Simulation using input data made by LHS, and case simulation with simple obstacles like red boxes here. And each simulation randomly is unique. You can see this video is very slow, but the guests meet the obstacle, they do not hit. They stop this. Slow down here, you can see. And the optimization is do like that. Basically, when a scenario occurs is set the same floor I mentioned before. And since we used about 50 scenarios as input, so we want to specify a smaller number of detectors. And the detector cost is set to 5 per detector, and total budget is set to 100. So maximum detectors is 20. And the placement like result is like example, example is like that figure. And cases reaching below the standard concentration was excluded. And the example, the placement is shown in the figure on the right. And with the surrogate modeling, the case of light air was simulated. A simple simulation was performed with Python, and a plate simulation was possible by reducing the loss value with a simple DNA model. With the detector placement optimization, like the risk at occurrence was set equal to 100, and on our scenarios were detected like that, and our risk score was less than 20. So confirming them, they are detected all. And the result of detector arrangement at this time is figure here. Here's some conclusion and future works. Against detector placement optimization framework using the surrogate model is proposed. Against this surrogate model was implemented with physics-based deep learning, and the detector placement can be optimized using the surrogate model and the higher mode MI and we currently only simple obstacles are implemented for the plan detector placement optimization framework will be developed that covers all possible scenarios while meeting the legal criteria. In the case of current detector placement, a risk-based optimization model was used. However, evaluation index for specific design of a risk score is needed in the future. Currently, we set the damage value is all same. We will develop the specific risk score. My presentation is
Okay, thank you. Any questions from the audience?
Just to have understanding on this detector, is this academic detectors or detector? Is this the detector that you are referring? Is this referring to the fire intent detectors or
it's for toxic gases. Toxic gases destruction.
toxic gases?
Yes.
So same for fire gases, right? So this simulation is to be done prior to the design, or this is something that will be done during any accident or any incident or the effort. Because in reality from industry perspective, right? So we have a guideline in order to do all this fire gas making. So they have their procedure based on FBI, calibrated but they have their procedure. In order to come out with so I just want to understand is this something that could be done if any incident happen, or is it something for the design?
Before the accident and after the accident or theft, we can
So if it is something that to be done before the design or prior to design, some sort of input for the design of the facility. So what exactly this simulation distinguish against typical scientific study that is done?
and we want the FNG system, FNG mapping system for using this.
Visually,
This is for design purpose.
yeah, sorry,
For design.
for design. Thank you.
Any other questions?
In the beginning, you showed some standards, right? As to how you place the detector location.
Yeah.
Do you think that your results here might improve the standards? Because the standards is if you have no method to calculate. So safe-wise, you just follow the standard, put detector here, 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 here.
Yeah.
So from your method, do you think there's a opportunity of changing the standards, for example, maybe making the detectors a bit further apart or less, or in your opinion?
We hope so. We hope so. The current standard is by distance-based. We propose the risk-based.
I know, but in your risk-based study, you think that you might improve the standards so that that is based on distance. You can improve optimize the distance.
Decrease the number of like having 4 or 5 in the same week. I had one question. One question in your slide. So in the surrogate modeling slide, can you go to that slide? The surrogate model explanation. Further, where you explain the how to generate surrogate model back initially. Yeah, this one. Yeah. So here you generate data using surrogate model or detailed model. What is the second step? The second, yeah.
This means
But that is you're generating data using the detailed model, right? Not the surrogate. That's the start.
So I have one line here. So since we are using a model to get some data, we know how accurate is that. It will be compared with safety simulation factor. Now we didn't compare with some safety model.
Okay, thank you. We need for the presentation and we'll have our next.